Did you know mirror images can be dangerous? Let me explain. Some biological molecules exhibit mirror images, or what is known as chirality. A very simple way to visualize chirality would be to look at your hands. They are both the same but mirror images with the same components. So you're probably wondering, if something has the same components but different positioning, how can that be dangerous? Well, since it has different positioning, it affects the overall outcome of potential reactions. The different geometric arrangement can have affinity for certain binding sites on substrates or your target molecule. In general, when we're talking about biological chiral molecules, we're generally talking about carbon-based chiral molecules. Usually it'll have a carbon binding to other constituents in that molecule. For example, a medicine you're probably familiar with, ibuprofen, has a pair of chiral images, also known as enantiomers. It has enantiomers noted as R-ibuprofen and S-ibuprofen. The R and the S nomenclature designates the molecular geometry configuration of the molecule based on the priority of the groups surrounding the carbon, known as constituents, and priority is determined by the atomic number. So R rotates clockwise while S rotates counterclockwise. The S-ibuprofen enantiomer is more active than the R-ibuprofen and provides the anti-inflammatory effect that it is well known for. However, R-ibuprofen is still included in the medication as the body can convert R-ibuprofen back into S-ibuprofen. So when you have compounds that contain both enantiomers, it is known as a racemic mixture. Racemic mixtures contain a variety of ratios based on the desired effect of your reaction. Now, let's take a look at naproxen. It is a non-steroidal anti-inflammatory drug, also known as an NSAID, abbreviated. So this is the example that is a prime example of being dangerous. So S-naproxen enantiomer is a good anti-inflammatory drug, while R enantiomer is toxic to your liver and is not approved for human consumption. Here's another fun fact about chirality. It also affects smells. For example, R-carvone smells like spearmint, and S-carvone smells like caraway seeds. Carvone is commonly used in aromatic essential oils and flavoring in certain products. So, you're probably also wondering, how do chemists actually know what enantiomers they have created if they visually cannot see them? Well, to test enantiomers, scientists can observe the optical rotation of said enantiomers, as they can rotate polarized light differently. As we have mentioned before, R rotates to clockwise while S rotates counterclockwise. So for the actual scientific methods they can use in the lab, they can use chromatography, X-ray crystallography, electrochemical testing, and just general behavior of enantiomers based on the environment they are in. And that's because enantiomers react differently, so they can determine which enantiomer it is. So yeah, chirality is important for life. If we didn't have the right ones, then life would be dramatically different than as we know it.